I'm just getting the engine ready to put back in now. I think I mentioned at the beginning that I'm not going to strip this engine down because I did a full overhaul on this around about 1500 miles ago, and I've replaced the top end about 300 miles ago. So, and I put that a borescope down the bores, and it looks completely clean, so it's not beneficial to take it apart. But I thought I'd just point out, as I'm cleaning the crankcase, maybe you can see the number 8 on the nut, on the bolt head, sorry. And that's probably alluding to that the bolt is an 8.8 grade. An 8.8 grade is like your standard grade. Okay. Now the next one up from that's a 10.8. And as you go up 10.8, 10.10s, 12.10s and things like that, the bolt becomes, the tensile strength of the bolts increases, which sounds fantastic. But what goes with that, though, with the increase of the tensile strength, is a reduction in the fatigue capability, especially where you've got relative movement between the parts. So what you do when you go to 12, 10, 10.10s and 10.8s and things like this, you're increasing the clamping pressure, right, between the component parts, which reduces the relative motion. Okay, again, sounds great. If you don't assure yourself of that, what happens is you get fractures of the bolt. Okay, and that's why, for example, slew bearing bolts on cranes are limited. I think they're limited to 10.8s from memory. It might be 8.8s, but I think they're limited to, certainly limited no more than 10.8s. And the reason for that is because if you don't, they fracture and they break. And I've seen this happen myself personally. A newly overhauled crane, I was called to do a quick inspection on it because they were fracturing bolts, and straight away, first bolt I picked up, it was clearly a 10.8 or whatever it was. It was the tensile strength was too strong. Its fatigue capability was just not there. So, bottom line is, for me, right, I would only ever fit 8.8 bolts unless it specifically states otherwise. So if you take out a 10.8 bolt, for example, on cylinder head bolts, where they want to reduce the diameter of the bolt coming down, and there are good reasons for that, to do with reducing the distance between you have between the bolt and the center line of the crankshaft. Then you must put the same bolt tensile strength back in. Right, let me carry on, clean it up. Don't know well you can see that, but this is another bolt I've just picked up, and again it's got the 8, and this just confirms it is an 8.8 bolt. Okay, and as I say, 8.8 is a standard one, and you can't go far wrong with that. I don't think there's a softer grade in there, but they're really good quality bolts. You just got to watch when bolts which aren't stamped, and typically they're coming from, foreign parts, let me put it that way. Not that they're all foreign parts, but they're less regulated, and there can be a lack of homogeneity in the bolt itself, which causes them to break more easily than they should do. So it's much better that if you do get bolts which have been properly graded, or you buy them from a reputable supplier, because obviously the cost of the impact from one breaking on a motorbike can be really quite severe. So update where we're up to. So we've got the brake disc fitted, got the brake lines, they're in, the splitter is in, we've got the horn mounting bracket on, the loom's in, although it's a bit short, so I need to figure out why. It's a bit short, so I need to figure out why it's short, but we'll have a look at that. What else have we got? Obviously all bits on the back are all on, including the tail unit. It's connected. What I need to do is move these two things. Is once I get the engine in, then I can start getting the arrangements fitted into these. Now they're all quite tired, so they don't really grip particularly well, so I'll have to figure out some way of doing that a bit better. But it's coming along. Yeah, so as I say, we've got to get the engine in. what I'm going to do is get the engine in, and then see these side covers, they've got to come off again because they do look very tatty, so they're going to have to be painted again. But yeah, so we're coming on. What I'll do is I've got various ways of getting engines in, and typically for an engine this size, because it's not particularly big, I'd manhandle it, right? But we are talking now getting towards the limit of what I can do. I mean, if you see the NSR 250 engine, that's super lightweight. It really is. It's got absolutely no problem manoeuvring that. But when we get to this, it's just getting to the limit of what I can do. So I'm going to try a new method of doing it, try and use my winch to help me. I mean, when we get to the size of, say, this thing here, when it's built, this is a GT550. This engine is so heavy, there's zero chance of me getting it in. Now what I normally do with these ones is I put the engine on the ground on its side, and I literally tip the bike over on top of it, and then bolt it in and then lift the bike up. If that sounds really Heath Robinson, it isn't, and it works really well with the Honda CB400F. I've done that multiple times. So that's the engine just in the frame. So this is the new method I use. So I use my winch here as a sky hook, attach this beam, and then just lifted it up here, and it kind of swung itself into the frame. So for this engine, you know, it's not particularly heavy. It worked okay. Yeah, I'd use this method again. For the heavier engines, I don't know, because it was a lot of work on my part. I think what I'll do is something different. Well, I don't know what that is. I mean, the ideal will be to kind of lift it up and kind of translate it in on a fork. But I don't know how to do it. So we've got the radiators on now, coolant water pipes attached, got the carbs in. Still working on the wiring loop. Christmas present from my daughter. So when I built this bike the first time, I replaced the self-cancelling relay with a standard one, okay, and just freaked the wiring so that it would run okay. I thought I'd go back to using the self-cancelling circuit. So first of all, I've got to test it to make sure it works okay. So how it works is that it's a standard relay, power in through this line here, and then it's earthed. It comes out, this stepped output goes through here, through the indicators. I've put two indicators on it, so there's a bit of load. This is if you haven't seen one before, if you're testing circuits, I really recommend you buy one of these. Not because of the stabilised voltage, which is extremely useful, but because it also limits the current. So if you do accidentally put a short in, right, it won't blow the crap out of everything. Okay, so I'm going to use my stabilised power supply to power the circuit, and if I switch it on, it should hopefully click. Right, so that's at work, and then what happens with the self-cancelling relay? The self-cancelling relay puts a positive signal down the cancel line, which is here. So if I touch this, it should stop. Stops. Comes on again. On. So that's working fine, right? So I can put this back in, give it a bit of a clean up, make it look new. But this is just for you, if you haven't seen one before. This is the control power supply. They're not expensive, these things, around about £40. Let's I think we can knock that. I'll leave it on. Right, so what you have is you have coarse and fine control of both the voltage and also the current. You know, I've set it'll self-limit itself in normal circumstances because of the resistance of the lights, obviously. However, as I say, if you are testing circuits and you're just not quite sure, it's good just to set quite a low current so you don't blow the crap out of everything. It's also good if you're testing electronic circuits as well, because you really do stand a chance of doing some damage there, especially if you're dealing with electronic equipment. Yeah, the thing's just stopped then.